Good afternoon. So, today is the fourth lecture in the series, and we will be talking about various types of flow examples. In the last couple of lectures, in the last 3 lectures rather, we have already talked about conservation of mass, then we talked about streamline, stream function, velocity potentials, rotational flow, potential flow. Now, with this much of information, and then we have discussed about relation between the velocity potentials and the stream functions. Now, with this background, let us clear our basics. Let us spend some time on working out some more examples, and that will give us a very good understanding about the flow characteristics. So, this we can start with this few examples. Before that, I will give you one of the relation that the stream function psi satisfies, particularly when the flow is rotational. When the flow is rotational, our stream function psi satisfies the Laplace equation. Satisfy Laplace equation. So, it is very easy. We know that we have the phi x is equal to psi y. Further, we know that we have phi y is minus psi x. If we now for a irrotational flow, for irrotational motion, we have u y is equal to v x, that is in 2 dimensional for 2 dimensional flow. So, if u y is v x, so now substitute del y, this is same as del y, u is phi x, here rather I will say u is phi x and v is equal to phi y. So, del y u is phi x, which is same as del y psi y, and again further we have we have v x is del v by del x, we have v is minus I x. So, this is equal to minus del square psi by del x square, and here also this also equal to del square psi by del y square. Now, from 1, and if we substitute for this 2 in 1, then what will happen? From 1 and 2 we will easily get this is u y is same as del square psi by del x square, del square psi by del x del y square, and v x is as minus del square psi by del x square. So, this will be plus del square psi by del x square is 0, which is nothing but the Laplace equation. So, this itself is the, and this is only possible when the flow is irrotational. So, that is very clear that when the flow is irrotational, we have both phi and psi satisfies Laplace equation. On the other hand, we have phi psi also exists when fluid is rotational, fluid motion is rotational, whereas phi does not exist, phi will not exist. For rotational flow. Rotational fluid flow. This is one of the very important characteristics of this streamlines and stream function. Now, I will give you another example. I will go to another example where we will talk about how to find the flow characteristics. Particularly, suppose I have been given a velocity vector q bar, I hat a x minus b y plus j hat b x minus c z plus k hat into c y minus a x. Then a b c are known constants and non-zero constants. They are non-zero constants. So, what will happen to the flow? Consider, characterize the flow. Characterize the flow. So, the first thing is that to check whether the flow is rotational, fluid is there is a fluid motion is possible or not. So, let us say that since it is independent of u v w rho, so you have to check that whether del u by del x plus del v by del y plus del w by del z, what happened to this. If we do that, so we have del u by del x, we have del u by del x u is x minus b y. So, it will be del u by del x is a and del v by del y plus 0 del w by del z, this is a z minus b y, this is a z minus b y. So, this is a z minus b y. So, this is 0 plus 0, here also 0, here also 0. So, this is 0. So, fluid motion is possible, fluid motion is possible and the flow is incompressible, fluid is incompressible. Now, again we will check for what will happen to flow vorticity vector, because if we can check that, we can find the what are the vorticity vector. In this case, what are the vorticity vectors? Vorticity vector omega bar. So, in that case we have omega x is equal to del w by del y minus del v by del z, del w by del y minus del v by del z. So, del w by del y is c minus del v by del z plus c, this is 2 c, and we have omega y is equal to del u by del z minus del w by del x. So, that will give us a del u by del z, del u by del z is a minus del w by del x is minus minus plus a, that is 2 a, and similarly we have omega z that is equal to del v by del x minus del u by del y. So, you have del v by del x is b minus b, that is plus b, that is 2 b. So, since omega x, omega y, omega z is non-zero, not equal to 0. So, flow is rotational. In this case, the flow is rotational, and once the flow is rotational, we can have a vorticity vector. So, omega bar exists, and once omega bar exists, then we can find what are the vorticity vectors, what are the equation of vortex lines. If we want to find the equation of vortex lines, that means dx by omega x is equal to dy by omega y, dz by omega z. If you do that, that gives us dx by your omega x is c is dy by omega y is a, and this is dz by omega z is b, which gives us. Now, if you like the first two members, then it will give us dx by c is equal to dy by a, and that gives us a x minus c y is equal to a constant. Call this constant as k1 say. And similarly, from the last two equations we can always get, we have dy by a is dz by b, and which implies az minus, which gives b by minus az is equal to another constant. Let this constant be k2. So, one equation is this, the other equation is this. So, the vertex and hence the vertex lines are the interest, hence the vertex lines are the intersection of 1 and 2. If I call this as 1 and this I call it as 2, intersection of 1 and 2. So, this is the way we will find the vertex lines. Now, I will go to another example. This is a very simple example. I will concentrate mainly today on various types of example. Given the velocity potential, suppose we have been given phi x y t. This is x minus t into y minus t. If phi is this, then what will happen to u? U is del phi by del x. U is del phi by del x, that will give us y minus t, and v is del phi by del y, that will give us x minus t. So, we have got u v, and we can, if you once u v is known, then what is the equation of the streamlines? That is dx by u is dy by v. These are the equation of the streamline. If these are the equation of the streamlines, then what will happen? This will give us v dx minus x minus t dx y minus t v u is y minus t dy, and that gives us x minus t square plus y minus t square is equal to constant. So, these are the equation of the streamline. These are the equation of the streamlines. So, and here the center of this circle is constant for various values of constant, we get a streamline, and here the center is just the time period t. Now, with this understanding, I will go to a one more example on this flow characteristics to understand the flow characteristics. Let me just say that suppose we have been given the velocity vector u, component of the velocity vector u is equal to x square. This is another example. U is equal to x square minus y square, and v is equal to minus 2 x y. Question is that characterize the flow. When the question comes to characterize the flow, we have to emphasize on few things. One of the thing is, that is the first of all, whether the flow is incompressible or compressible, or whether there is a possible fluid motion, and once the fluid motion exists of a particular nature, we need to know what are the streamlines, because that will give us the flow direction. Then once we know the streamlines, then we need to know whether the flow is rotational, and if the flow is rotational, then we find the velocity potential, and if the flow is rotational, then better to find out what is the vorticity vector, because that will give us the direction of the flow in the angular motion of the flow. So, these are the things. So, in this case, so to understand this first, when we say characterize the flow here, the question is itself, and first of all we have to say whether there is a fluid motion. So, for that we need to know what is del u by del x plus del v by del y. First thing is to check that whether this is a two dimensional motion, the problem is two dimensional in nature. So, flow is two dimensional. So, we have this. So, we have del u by del x, and that is del u, which implies del u by del x is 2x, and del v by del y is minus 2y minus 2x is 0, and since this is 0, so there is a fluid motion possible and flow is incompressible, that itself. So, that itself clarify that the motion of a incompressible fluid exists. There is a flow of incompressible fluid, incompressible, that fluid is incompressible, rather we got it, fluid is incompressible. Now, with this, now whether to check whether the flow is what about the vorticity vector, because that will give us the vorticity vector. If you look at the vorticity vector, there is a del v by del x minus del u by del y, and this is equal to del v by del x minus 2y and minus del u by del y. So, this is minus minus plus 2y, this is 0. So, del v by del, so that means omega z is 0, 0. So, which says that flow is irrotational. Once these two things are known, that flow is incompressible and irrotational, obviously the next question is come to know the streamlines. So, to know the streamlines, we have to first look at the equation of the streamlines. So, equation of the streamlines are dx by u dy by v, and that gives us dx by x square minus y square is dy by minus 2 x y. If this is, and then so which simplifies to, I will just simplify, that will give you 2 x y dx plus x square minus y square dy is equal to 0. Since we are looking for streamlines, then here if I call this as d psi, then what will happen to my psi x? My psi x is 2 x y and my psi y is x square minus y square. If psi x y is 2 x, which implies means psi, I will take 2 x y. So, this will be x square y plus f of y, where is an arbitrary constant. On the other hand, if psi y is x square minus y square, then my psi is equal to, this is x square y minus y cube by 3 plus some another function of x, because this is a derivative with respect to y. So, that will give us another function. So, now if we compare a and b, because a gives an representation of psi, b also gives an representation of psi, and here that will give us that from these two we get is f y equal to minus y cube by 3, and also what will be g x? G x is 0, which implies my psi x y is x square y minus y cube by 3, and this psi x y, if this is psi x y, then this is constant, gives us the streamline. These are the streamlines. So, this is better to go by this way, because otherwise if you go by try to directly sum, there is a little complexity, you will get this answer, but there will be little complex. So, here better go by psi x is 2 x y, go for psi, and psi y is this, which is go for, and this will give us the streamlines in a very easy manner. Now, with this I will go for now already we have now worked out a few examples. With this now let us concentrate on few. One of the things is that what is the boundary surface. Let us know what is a boundary surface and what are the conditions satisfied on a rigid boundary or a moving boundary. If let me say that this is a boundary surface. So, what will happen? Let me take a point P. So, there is I consider the top side is the boundary, it is with the fluid. So, let me take a point P here. Once I have a point P, let me draw two things. Let me call this surface as f is a function of r bar on t, because there is a fluid is flowing and f is this is a P is a point here and f is the boundary surface. This surface I call it this is satisfied f of r bar t, where the fluid velocity is q bar and the surface velocity, this is the fluid velocity and let u bar is the surface velocity. So, now at this point, so there will be a fluid velocity, that is q bar, and let the surface velocity be u bar. So, fluid is moving with velocity q, the surface itself is moving with the velocity u bar. Let n hat be the unit normal from this point in the outward direction. So, if this has to be a boundary surface, if this surface has to be a boundary surface, what is the normal component velocity of the fluid, that is q bar dot n hat has to be the same as normal component of the velocity of the surface. So, this is the normal component. So, that will be u bar dot n hat. So, at a boundary surface this condition has to be satisfied, because this is the normal component of the velocity of the fluid particle at the point, this is the normal component of the surface. And if now further f is the surface, this surface is f. So, if I call this surface, this is by 0. So, what will happen if this is the surface given by f of r bar t is 0, and what is grad f? Grad f will is the normal to the surface f of r bar t is 0. F of r bar t is 0. If this is the normal to the surface, now we have n hat is parallel to grad f, because we have n is the unit normal and grad f is normal to the surface. So, both are parallel. So, because of this we can always say from this A, from A we can always say that we have q bar dot grad f is same as u bar dot grad f. So, these two has to be same. Once these two are same, now let the point because this is a moving surface. So, the point, let us say that after time delta t, the points move to the p moves to q, and here when p moves to q, then the new point at the point q, at q the surface becomes f of r plus del r t plus del t, because assuming that there is a shift of the time with a change in time t del t, let there be a change in the position is del r. So, at q again we have f of, because this is the surface. So, f of r plus del r plus comma t plus del t is a 0, and if that is 0, then that itself is gives us f of r t, which is same as, or rather which implies f of r t plus del r dot grad f plus del t dot del f by del t. This is a cross, this is not cross dot product, it is multiplication, this is 0. Now, and already we have f of r t is 0. If f of r t is 0, then this term will give us 0, and so this is 0. So, we have got del r dot grad f is del t into del f by del t. Rather put it, it is not dot product, this is just multiplication. Now, with this, now if we go back to this, then we have, now take the limit. If you look at the limit, so we have del r by del t, we have del r by del t dot grad f is equal to minus del f by del t, and what is, so limit. So, if you take the limit del t tends to 0, del r by del t, that is nothing but into grad of f, that is again same as minus del f by del t, and this is what, look at this, this is nothing but, we have already talked about, this is dr by dt, dr bar by dt dot grad of f, this is minus del f by del t, and which is same as, and since r bar is a position vector of the surface, then we have dr bar by dt gives us u bar. So, we have u bar dot grad of f is minus del f by del t. Now, this is a very important result. So, now we have already seen that, so which is same as u bar dot grad f is already we have seen in the, we have u bar dot grad f can be written as q bar dot grad f. So, which implies q bar dot grad f equal to minus del f by del t. So, it implies del f by del t plus q bar dot grad f equal to 0, which nothing but which is same as df by dt is equal to 0. That means, if f is the surface, it is a boundary surface, then we have on the boundary surface df by dt is 0. This is a very important result, which is always used, particularly when we have a boundary surface. Now, which is same as already d by dt is the, where d by dt we know this is the material derivative, and again if I simplify this, if the surface becomes rigid, which gives if the surface is becomes rigid, then we have del f by del t is 0 and this becomes u del f by del x plus v del f by del y plus w del f by del z. And which gives me, and so the normal component of the velocity for the boundary becomes q bar n hat becomes q bar dot n hat is grad f by grad f modulus, and that is, and this q dot grad f becomes del f by, because df by dt is 0. So, q dot grad f becomes minus del f by del t minus del f by del t divided by this becomes the this is your q bar dot n hat. So, we have two things, that is the normal component of velocity on the boundary surface, and again we have already shown that q bar on the boundary surface, if this is 0, then q bar dot n hat is 0 if the boundary is fixed. So, this is for fixed boundary. This is another important result, that how to get the boundary surface, and if we know the boundary surface and if the boundary is fixed, then you have q bar dot n hat is 0. That is now with this I will go to a very nice example. Now, suppose I have been given the velocity vector u is equal to minus a. In fact, this kind of problems comes in water waves, y plus h sin k x into sin omega t, and my v is a sin hyperbolic k into y plus h into cos k x into sin omega t. If these are the UV, so basically this UV represents is a standing wave in water, or a basically standing wave in water, particularly in it is a problem related to water waves. basically it is a standing wave. It can be easily seen that here del v by del x plus del v by del y equal to 0. It can be easily checked this. Further, you can find easily that your u v del v by del y equal to minus del v by del x, sorry, plus del v by del x. So, here it shows the fluid is incompressible. Here the fluid is incompressible, and again our flow is rotational, motion is rotational. Our fluid motion is rotational. Once these two things are satisfied, then we can easily find out that so what is our velocity potential u? Our velocity potential, because we have to find our velocity potential or streamlines, and because already flow is rotational, so there is verticity vector will be 0. So, we will have to only find what is the velocity potential phi and what are the streamlines, and accordingly the stream functions. So, if we are to find phi, we have been already given, we have phi u have been given. So, u is nothing but phi x is minus a cos hyperbolic k into h plus y sin k x sin omega t, and which implies phi is equal to, we have phi x a by k cos hyperbolic k into h plus y into cos k x sin omega t plus f of y. Again from this is u is equal to phi x. Further from we have been given v is equal to phi y, which is already given to us, that is a sin hyperbolic k into h plus y into cos k x sin omega t, and which implies my phi becomes, I have to take the derivative with y, becomes a by k, this is cos hyperbolic k into h plus y into cos k x sin omega t, and which implies plus here it can be a constant of g of x, because the expression for phi, this part is same as this part. So, my f y and g x has to be 0, because there has to be a constant is equal to constant, and that constant can be taken as 0 without loss of generality. So, we have got what is phi, and once we know phi, then easily can, and this is very important, because this phi, there is a relation in water waves, that is phi t, if you phi t plus zeta, or we can say eta t is a phi y, that is on y is equal to 0, and where eta is the free surface. Suppose this is the depth of water, this is what, if this is the mean free surface, that is y is equal to 0, and here it is the depth of water, and then we can say this is y is equal to eta x t. We have just derived that on this surface, it can be easily shown that in the linearized case d by dt, because y is equal to eta, y minus eta x t 0, this is a boundary surface, because it is the surface of the fluid. So, on this surface it is 0, just now we have derived a boundary surface d by dt of this is 0, and that will be, that is satisfied on y is equal to eta, and assuming that eta is small, if eta is small, if we can say that eta is small, then it can be proved that this condition becomes eta t is equal to phi y is satisfied on y is equal to 0, and that is the again the called the kinematic condition on the free surface of water. I will come to this a little towards the end when I will come in detail about water waves, and because what I say that this once we know the velocity potential phi, we can know what exactly is our free surface, and this free surface, because we know eta t is phi y, already have been given phi y, and then we can as if we know what is eta, and that is again on y is equal to 0. So, this way knowing the velocity potential, we can always come to the know what the free surface is. Once we know the velocity potential and the free surface, then if I have any structure here, then I can always calculate the pressure that is acting on this, basically the fluid on this structure, what is the pressure. So, I can always calculate the pressure. So, this is that is why it is very important to know the velocity potential, and stream like the stream functions is important because it gives us the streamlines will give us the flow direction. Similarly, the velocity potential for potential flow, the velocity potentials are very important because this velocity potential gives us that we utilize this to get the free surface elevation. Sometimes we use this even if to calculate the force, because we can calculate the pressure by using the Bernoulli's equation. I will come to those things in detail later, because there is a equation for a rotational flow, equation of motion lead to Bernoulli's equation, and that from there we can calculate the pressure at each point, and once we know the pressure at each point of the fluid, basically what we call this, we will call this as the hydrodynamic pressure, and once we know the pressure, we can always calculate the force. So, I will come to those equation of motion in my next lectures, and once we know this, then after knowing the equation of motion, Bernoulli's equation and other things, then at the towards the end I will come in detail about water waves. So, now already we have been aware of when the fluid is incompressible and the motion is irrotational, and also another aspect we have not yet emphasized, that is when the fluid is inviscid. So, if the fluid is inviscid and incompressible, this is another point to be noted. I will come to this later because I have not yet talked about viscous fluid. So, when the fluid is inviscid and incompressible, we will say that, and in practice there are very few situations where we will come across a fluid which is very 100% inviscid or 100% incompressible, but for simplicity of the modeling, many fluids we can always under this assumption of incompressibility and assuming the fluid is inviscid, large number of problems can be handled, and this is that is why this kind of fluid is called a ideal fluid. Fluid where the fluid is inviscid and incompressible, we call them as ideal fluid. Now, already in fact, most of the derivations we have done as of date, as of now, is based on the Cartesian coordinate system. Cartesian coordinate system. Without going to detail, I will just say what happen if we are looking at polar cylindrical polar coordinate system. This equation of motion I will not go to the details, it can be derived, there are many textbooks, you can go through this and independently it can be derived. But however, I will just say that what will happen, suppose we have a very important result, that is the relation between phi x is equal to psi y and phi y is equal to minus psi x. Let me say what will happen to these equations, what we call the Coserimon equations, and that is the relation between the stream function and the velocity potential. If what will happen, if it is suppose I say x is r cos theta and my y is r sin theta. If I take this, what happened to the flow? What happened to these phi x's, psi y and phi y's? So, it can be easily, because the derivation, what is del phi by del r? Let me see, because what is the corresponding form in r theta coordinate? It will, if you look at del phi by del r, basically this is done in this way, del phi by del x into del x by del r, because plus del phi by del y into del y by del r, and that gives us del phi del x by del r. Del x by del r is cos theta, del x by del r, del x by del r is cos theta into del phi by del x. So, I can always write r del phi by del r is equal to r cos theta del phi by del x plus del phi by del y, del phi by del y by del r is sin theta. So, it can be r sin theta into del phi by del y. Similarly, if you look at what happened to del phi by del theta, because I am del phi by del theta is same as del phi by del x del phi by del x into del x by del theta plus del phi by del r into del r by del theta, and this gives us del phi by del x by del theta, del x by del theta is minus r sin theta into del phi by del x. Then if I have del r by del theta, sorry, this is x, this is y, so del y by del theta. So, this is minus r sin theta del phi by del x plus del phi by del y is r cos theta plus r cos theta into del phi by del y. So, once we have, now we know that del phi by r del phi by del r is r cos theta del phi by del x plus r sin theta del phi by del y. On the other hand, you have del phi by del theta is minus r sin theta del phi by del x into r cos theta plus r cos theta del phi by del y. Now, in a similar manner, what will happen to, now if I go back to r del phi by del r, which is nothing but r cos theta del phi by del x plus r sin theta del phi by del y. Now, what I will do, del phi by del x is phi x is psi y. So, I can always write r cos theta del psi by del y. Then what is, then del phi by del y is minus del psi by del x. So, this is minus r sin theta into del psi by del x. Now, if I relate it, r cos theta, if I go back to my previous page, my del phi by del theta is minus r sin theta del psi by, this I can call it as del psi by del theta, because in the previous page I have seen del phi by del theta. So, if I replace phi by psi, because I know my del psi by del theta will be minus r sin theta del psi by del x plus r cos theta del psi by del y. So, that will give me r del phi by so, hence I get. In a similar manner, I can easily get, if I proceed in the same way, I will get it my del phi by del theta, I will get minus r sin theta del phi by del x plus r cos theta del phi by del y, and that will give me minus r sin theta minus r sin theta del phi is del psi by del y plus r cos theta del phi by del y is minus I x minus del psi by del x, and that I can call it minus r minus times r sin theta del psi by del y plus r cos theta del psi by del x, and I have, if I go back to my del phi by r cos theta del psi by del x plus r sin theta del psi by del y, that is nothing but minus del psi by del theta minus r del psi by del r. Hence, from these two I will get my del phi by del theta. This is one relation, that means giving me del phi by del theta is minus r del psi by del r, and here from here I get, which is same as r del phi by del r. So, these two equations are the corresponding equations of the shear equation, Coserimon equations in the cylindrical polar coordinate. In a similar manner, we can always say that what will happen to the equation of continuity in cylindrical polar coordinate. We just take x is equal to, in the cylindrical we will take x is r cos theta, y is r sin theta, and z is equal to z. If you take this, we can similar manner we can always derive what are the continuity equation. Rather, these things I leave it as a homework, continuity equation, and derive the continuity equation. You can derive the vertex streamlines, vertex line, verticity vector, and stream vertex lines in cylindrical polar coordinate. So, this can be done, and I am not going to the details of this. This everyone it can be tried at home. It is very interesting to do this exercise. With this, I think I will stop today, and next class we will not talk more about this, because we will rather use this in the coming classes. We will concentrate on particularly in the next class I will talk to, we have not yet talked about the motion, because forces, what are the forces acting on a fluid, and what about the fluid motion. There is something called equation of motion, we will come to that, and that is based on the law of conservation of momentum, basically the Newton's second law. We will come to this in the next class. Thank you.